All right, so get ready because today we're going deep on one of the most famous experiments in physics,
Oh, yeah.
the double slit experiment.
Definitely a classic.
You know the one where electrons act like they're going through two places at once?
Right. It's a classic for a reason.
Mm-hmm.
I mean, it really shows how strange and amazing the quantum world is.
For sure. But what if I told you we're looking at a theory
Okay.
that tries to explain this experiment
Yeah.
without relying on the usual quantum mechanics stuff,
Okay.
like wave functions?
That's right. We're going to explore a model that uses something called a push wave.
Okay.
And this push wave is created by the interaction of a subtle magnetic field,
Okay.
or SMF,
SMS.
and the relative vacuum of space, which they call RVS.
Okay, hold on. Subtle magnetic field and relative vacuum of space.
Yeah.
Those sound a little bit,
A little out there.
out there. Can we break those down a bit?
Absolutely. So we're all on the same page.
Yeah, think of the SMS as like a deeper, more fundamental kind of electromagnetism.
That, permeates all of space. It's always there.
Uh-huh.
But we just don't usually notice it.
So like a hidden layer of electromagnetism underneath everything else.
Exactly. Now, the RVS is a bit trickier.
Okay.
It suggests that the vacuum of space isn't actually empty,
Okay.
but has variations in its pressure.
Hmm.
Kind of like a subtle texture.
Okay. That's a pretty different way of thinking about empty space.
Yeah.
So how did these two things create this push wave that supposedly guides the electron?
Well, the theory proposes that the SMF interacts with the RVS.
Okay.
And this interaction creates the push wave. Imagine the electron riding this wave as it approaches the two slits.
Okay, I'm starting to get the picture. Now, I know there's an equation in the source material that describes all of this,
Right.
but to be honest, it looks pretty intimidating.
I hear you, equations can be a bit much.
Yeah.
The important thing to understand is this equation basically tells us how strong the push wave is.
Okay.
And that's based on the strength of the SMF and the RVS at any given point.
Yeah.
So stronger SMF or RVS means stronger push wave.
So the math is essentially saying that the push wave is shaped by this underlying interaction
Yeah.
between the SMF and the RVS. But how does that explain the interference pattern?
Okay.
You know those light and dark bands we see on the screen?
Right, the interference pattern. Well, this theory says that as the push wave goes through the two slits,
Yeah.
it splits into two separate waves, one from each slit these waves, then overlap and combine on the other side.
Like ripples in a pond where the waves either add up or cancel each other out.
Exactly. Where the waves line up, their peaks and troughs reinforce each other,
Yeah.
creating a stronger wave.
Yeah.
And that's a bright fringe on the screen where they're out of sync. They cancel each other out, resulting in a dark fringe.
Got it.
That's how the theory explains those iconic bright and dark bands.
So the interference pattern isn't created by the electron itself,
Right.
but by this push wave that it's riding on.
That's the idea. And there's another interesting piece to this puzzle.
Okay.
A scaling factor called Fibonacci scaling that might influence the strength of these waves.
Fibonacci scaling, I've never heard of that. What does it do?
It's a bit complex, but essentially it introduces a sort of fractal element into the mix.
Mm-hmm.
It suggests that the push wave's amplitude
Okay.
might change over time in a way that's determined by this fractal scaling factor.
Okay.
Think of it as a subtle ripple effect that could influence the overall pattern.
So this Fibonacci scaling adds another layer of complexity to how the push wave behaves.
Exactly. Now, in a typical double slit experiment, this scaling factor is probably pretty small, so we might not notice its effects.
Okay.
But the source material hints that in certain scenarios, especially those involving longer time scales
Uh-huh.
or more complex setups, it could become much more significant.
Okay. Now I'm really curious. It sounds like this Fibonacci scaling could lead to some pretty unexpected results.
It could.
But let's come back to that later. For now. I'm still trying to wrap my head around this idea of a push wave guiding the electron.
It's definitely a different way of thinking about things.
Yeah.
But that's what makes it so intriguing.
I'm with you on that, but there's one big question I have to ask.
Sure.
What happens when we try to measure which slit the electron actually goes through?
Okay.
Doesn't that mess everything up?
That's the million-dollar question in quantum mechanics. And this theory offers a very specific answer.
Okay. Hit me with it. What does this push wave model say about measurement?
It proposes that when we try to measure the electron's path,
Yeah.
we're not actually collapsing the wave function like traditional quantum mechanics says. Instead, we're physically disturbing either the SMF or the RVS near the slits.
Hold on, you're saying that the act of measurement itself, just by trying to look at the electron, actually changes the environment around it.
Precisely. And that disturbance in the SMF or RVS messes with the push wave, essentially forcing the electron to choose one path or the other.
So the interference pattern disappears not because we've magically known which path the electron took, but because we've physically disrupted the system.
Exactly. It's like sticking your finger in a perfectly still pond and disrupting the ripples. The measurement itself becomes part of the experiment, influencing the outcome.
Wow, that's a pretty radical idea. So in this model, we're not just passive observers, we're active participants shaping the reality of the experiment just by trying to measure it.
That's one of the key takeaways from this theory. It suggests that the active measurement has a real physical impact on the quantum world. And it does so by affecting these underlying fields, the SMF and the RVS, which in turn shape the behavior of the push wave.
This is blowing my mind. It's still strange and counterintuitive, but it feels a bit more tangible than the traditional quantum mechanics explanation. We're not talking about collapsing wave functions or consciousness playing a role, but about real physical interactions happening at a level we don't usually see.
I agree. It offers a different lens through which to view the quantum world, one that's perhaps a bit more grounded in our everyday experience.
This is fascinating stuff, but we've only just scratched the surface before we dive deeper. Let's take a quick... We'll explore more about this relative vacuum of space, this RVS, and how it fits into the big picture.
Sounds good.
Stay with us. Welcome back. We're in the middle of exploring a truly mind-bending take on the double slit experiment.
That's right.
So far, we've learned about a push wave guided by something called the relative vacuum of space, or RVS.
Right.
But I think we need to spend some time really understanding what RVS is.
It's definitely one of the most intriguing aspects of this theory. You see, we tend to think of the vacuum of space as being completely empty nothingness.
Okay, I'm all ears. How can nothing be something?
Well, imagine the vacuum not as empty space, but as a sort of dynamic medium, almost like a fluid.
Okay.
And just like a fluid can have variations in pressure, so too can this vacuum.
Sure, saying the vacuum of space has pressure. That sounds a bit counterintuitive.
Right.
How can empty space exert pressure?
It's a bit hard to wrap our heads around because we're used to thinking of pressure as being caused by molecules bumping into each other.
Yeah.
But in this theory, the pressure arises from the inherent energy fluctuations of the vacuum itself. Quantum physics tells us that even in a vacuum, there are always tiny fluctuations of energy popping in and out of existence.
So these energy fluctuations are what create the pressure of the vacuum.
Exactly. And it's the variations in this pressure, the unevenness, if you will, that we're calling the relative vacuum of space, or RVS.
Okay.
It's like the vacuum has a subtle texture, a landscape of peaks and valleys of vacuum pressure.
This is where my brain starts to melt a little bit. Okay, so we have this vacuum with pressure that varies from place to place. How does that tie into the push wave that's guiding the electron?
Well, that's where the subtle magnetic field, or SMF, comes in.
Yeah.
But we talked about it being like a deeper layer of electromagnetism.
Yeah.
The theory suggests that this SMF interacts with the RVS, and it's this interaction that gives rise to the push wave.
Okay, so the SMF is like the wind blowing over the textured surface of the RVS, and that creates the wave.
That's a great analogy. The SMF provides the force, and the RVS, with its variations in pressure, determines how that force is shaped into a wave.
So the push wave is like a collaboration between the SMF and the RVS, but I'm still not clear on how this explains why measuring which slit the electron goes through destroys the interference pattern.
Right. Remember we talked about how, in this model, measurement doesn't collapse the wave function, but instead disrupts the system physically.
Yeah, it's like we're messing with the delicate dance of the electron by trying to observe it.
Exactly. Now imagine this. When we try to measure which slit the electron goes through, our measuring device introduces a disturbance in the RVS near the slits. It's like creating a tiny ripple in the vacuum pressure right where the electron is trying to pass through.
So we're not just observing the electron, we're actually changing the environment it's moving through.
That's right. And that disturbance in the RVS disrupts the push wave, essentially forcing the electron to pick one slit or the other. It's like placing a small obstacle in the path of the ripples in our pond analogy.
So the interference pattern disappears not because we've magically known which path the electron took, but because our measurement created a real physical disturbance in the vacuum itself, which in turn disrupted the push wave.
Exactly. That's a chain reaction.
Okay.
Our measurement disturbs the RVS, which disrupts the push wave, which then alters the path of the electron, ultimately leading to the disappearance of the interference pattern.
That's pretty mind-blowing. It's almost like we're participating in creating the reality we observe just by the act of measuring.
That's one of the profound philosophical implications of this theory. It challenges the traditional view of the observer as being separate from the observed.
Yeah.
In this model, we're intimately interconnected with the quantum world, and our actions have real physical consequences.
That's a huge departure from classical physics, where the observer is supposed to be objective and detached.
Right.
But if this model is correct, it seems like that separation is an illusion.
Yeah,
We're part of the system, whether we like it or not.
exactly. And it raises all sorts of fascinating questions about the nature of reality and the role of the observer. But before we get too deep into the philosophical weeds, there's another element of this theory that I think we should explore. Remember that Fibonacci scaling we talked about earlier?
Oh, yeah, that fractal scaling thing you said, it could play a significant role in certain scenarios.
That's right. Now in a standard double-slit experiment, the time scale is so short that the effects of Fibonacci scaling are probably negligible.
Okay.
But what if we were to conduct an experiment on a much longer time scale, or with a much more complex setup?
Okay. I'm intrigued what could happen then.
Well, remember, Fibonacci scaling introduces a fractal element, meaning the behavior of the system is influenced by its own past behavior in a complex way. If the experiment were to run for a very long time, or if the setup were intricate enough, this fractal scaling could start to have noticeable effects. We might see changes in the interference pattern that we wouldn't expect based on standard quantum mechanics.
So it's like the longer the experiment runs, the more this fractal memory of the system starts to influence the outcome.
Exactly. And there's one type of experiment where this could get particularly interesting, those delayed choice experiments we touched on earlier.
Right. The ones where we decide whether or not to measure which path the electron took after it's already gone through the slits.
That's the one. Now, imagine this in a delayed choice experiment. The fractal iteration, which determines the influence of Fibonacci scaling, might actually shift mid-experiment, depending on the choices we make.
Hold on. So you're saying that the choices we make in the present could potentially influence the way the system behaved in the past?
That's the implication. And it's one of the most mind-boggling aspects of this theory. It suggests that time might not be as linear and straightforward as we think.
Yeah.
If Fibonacci scaling is at play, the past, present, and future could be more interconnected than we ever imagined.
Wow, that's heavy stuff. It's like the universe is constantly readjusting itself based on the choices we make, even choices that seem to be made after the fact. But this is all still theoretical, right?
Of course, we're exploring a model that, while fascinating, is still highly speculative. But that's the beauty of theoretical physics. We can explore these what-if scenarios and see where they lead.
I'm definitely hooked on this what if, but before we spiral too far down the rabbit hole of time and choice, I think we need to take a step back and consider the practical side of things. If we entertain the possibility that this theory is correct, what kind of experimental evidence would we need to see to give it more weight? What kind of test could we design to put it to the test?
Those are excellent questions, and ones that will take us even deeper into the implications of this model. Let's tackle the challenges of testing this theory and explore what its validation could mean for our understanding of the universe.
Welcome back to the deep dive. We've been on quite a journey today exploring a truly radical interpretation of the double slit experiment. This push wave model, with its subtle magnetic field and its relative vacuum of space, really challenges how we think about the quantum world.
It certainly does. We've gone from questioning the nature of empty space to pondering the role of fractal scaling in the fabric of reality.
But before we get too carried away with the philosophical implications, we have to ask, how do we actually test this theory? It's all well and good to have these mind-blowing ideas, but without experimental evidence, they remain just that, ideas.
You're absolutely right. The scientific method demands that we put our theories to the test, no matter how elegant or intriguing they may seem.
So if we were to design an experiment to validate this pushwave model, what would we be looking for? What kind of evidence would convince even the most skeptical physicist?
Well, one promising avenue would be to look for tiny deviations in the interference pattern of the double-slit experiment. Standard quantum mechanics predicts a very specific pattern. But this theory suggests that variations in the SMF or the RVS could cause subtle shifts in the spacing or intensity of those bright and dark bands.
So we're not just looking for the presence of the pattern, but for subtle anomalies that wouldn't be explained by conventional quantum mechanics.
Exactly. It would be like finding tiny imperfections in a seemingly perfect diamond imperfections that reveal a hidden layer of complexity.
But wouldn't those deviations be incredibly small? Maybe even too small to measure with our current technology?
They might be, but that's where the challenge and excitement of experimental physics lie. We're constantly pushing the boundaries of measurement precision. And if we could correlate these subtle shifts in the interference pattern with changes in magnetic fields or vacuum conditions, that would be a major step towards validating this theory.
I can see how that would be compelling evidence. It would be like saying, look, when we tweak the SMF or the RVS, the interference pattern changes in exactly the way this model predicts.
Precisely, it would establish a clear link between these underlying fields and the behavior of the electron, providing strong support for the idea of a push wave guiding the particle's path.
But what about those delayed choice experiments you mentioned earlier, that they could play a key role in testing this theory, especially when we factor in the concept of Fibonacci scaling?
Ah, yes, delayed choice experiments. They're already mind-bending enough in the context of standard quantum mechanics. But when you add in the idea of Fibonacci scaling with its fractal influence across time, things get really wild.
Remind us how delayed choice experiments work. It's been a lot to take in.
In a nutshell, in a delayed choice experiment, we decide whether or not to measure which slit the particle went through after it's already passed through the slits. It's like we're making a decision that seemingly affects something that's already happened.
Right. It's as if the universe is playing catch up with our choices.
Exactly. Now, this theory proposes that the choice we make in the present, whether to measure or not, could actually influence the way the system behaved in the past, thanks to the influence of Fibonacci scaling.
So you're saying that the interference pattern we observe isn't just a consequence of what happened at the slits, but also of choices that we make later on.
That's the idea, and this is where things get really interesting, because if that's true, it means that time might not be as linear and straightforward as we think. It opens up the possibility that the past, present, and future are more interconnected than we ever imagined, all influenced by this fractal scaling factor that weaves its way through the fabric of reality.
Whoa, that's a pretty profound implication, but it also sounds incredibly difficult to test experimentally. How could we possibly prove that our choices in the present are influencing the past?
It would definitely be a challenge requiring meticulously designed experiments that can isolate the influence of Fibonacci scaling from other factors. But it's not impossible. One approach might be to look for subtle correlations between the choices we make in the delayed choice measurement and specific features of the interference pattern. For example, if we consistently observe certain anomalies in the pattern when we make a particular choice, and those anomalies disappear when we make a different choice, that would be a strong indication that something very strange is going on.
It's almost like we'd be looking for signatures of Fibonacci scaling in the interference pattern signatures that are directly linked to the choices we make in the present.
That's a great way to put it. It would be like finding a hidden message encoded in the very fabric of reality, a message that reveals the interconnectedness of time and the profound influence of choice.
This has been an absolutely mind-blowing deep dive. We started with a simple question: how does the double slit experiment work? And we ended up on a journey that took us from the nature of empty space to the potential for time-bending choices.
It just goes to show that one seemingly simple question can lead us down a rabbit hole of fascinating and unexpected discoveries.
And who knows where this path will ultimately lead? Perhaps this push wave model with its radical implications will one day be validated by experiment, ushering in a new era of physics where the seemingly impossible becomes the new reality. Or maybe it will remain a fascinating but ultimately unproven theory, a testament to the power of human imagination to explore the boundaries of what we know and what we think is possible.
Either way, the journey itself is worthwhile. It's through these explorations, these leaps of imagination, that we expand our understanding of the universe and our place within it.
Thank you for joining us on this deep dive. Keep those minds open, stay curious, and until next time, keep exploring the wonders of the universe.